Hello, I am Matt Helmers, an associate professor in the Department of Agricultural and Biosystems Engineering at Iowa State University. This is the first of 8 drainage water management training modules. The first module that we're going to go over today is the background on drainage and water quality, and there will be subsequent modules, and we'll talk just briefly about those as we go through. A different developer for each of these modules, but the first one, again, is on the background of drainage and water quality. Just to highlight the different modules that we have. Again, the first one here on the background in drainage and water quality. Next, we'll have drainage concepts and tools developed by Chris Hay. Drainage water management planning process developed by Kelly Nelson. Then drainage water management concepts and land suitability developed by Dr. Richard Cook. Then the water control structures developed by Tom Scherer. The drainage water management layouts, new and retrofits, developed by Gary Sands. Drainage water management operation and management, developed by Larry Brown. And related conservation drainage practices, developed by Jane Frankenberger. So we'll get started on the history of drainage. As we look at drainage, subsurface drainage has been critical to the development of our agricultural systems in the upper Midwest U.S., really in many areas of the U.S., but particularly up in the upper Midwest, as we'll talk about a bit more as we go through this. As we look at drainage, or subsurface drainage, it really began in the U.S. in the 1800s in New York State, and John Johnston is recognized as the father of drainage in the U.S. Actually, there's a drainage museum at his home place in New York. As we look at drainage throughout a lot of the U.S. and the Midwest U.S., critical act was the Swampland Act, or Acts of 1849, 1850, and 1860. Granted swamp and overland flow lands to the states for reclamation, and this led to drainage for settlement and development. So kind of around that 1800 is when we started to see some drainage in the upper Midwest, and then it really took off as we got to the late 1800s, early 1900s in many areas. As we look at Iowa, where I'm from, right around 1900 is when a lot of our drainage districts were established, and so a big push and a lot of installation of artificial drainage systems at that time period. But as we look at it historically, about that 1860 period, we kind of saw the start of drainage, and a lot of that coming from the Swampland Acts. And just a photo of John Johnston at the time, or about the time that he originated tile drainage in America. So as we look at our drainage goals and goals of our drainage system, the goals are really to aid crop production. If it wasn't to aid crop production, we probably would not have the extensive drainage network that we have. And really it helps us with crop production by providing for site trafficability, for timely planting and harvesting, and also for lowering the water content in the root zone to provide adequate aeration following excessive rainfall. For example, in Iowa, we get a lot of our rain in April, May, and June. We get high water tables then during that time of the year because of the rainfall. Our artificial drainage allows us to lower that water table to allow for crop planting, early crop germination, and early crop development. So that drainage is very critical to getting some air back into that soil profile for the crop development. So as we look at drainage, our goals are really to help aid in crop production. However, if we take a broader view of this, certainly the situation, we have a demand for our agricultural products. Throughout the Midwest, really throughout the world, there's a demand for agricultural products, but at the same time, we have an increasing concern for local and regional waters. Two of those are hypoxia in the Gulf of Mexico, and then increasing concern about phosphorus loading to Lake Erie or the Great Lakes basin, and the role of drainage in this loading. So as we look at hypoxia, the Hypoxia Task Force in their Hypoxia Action Plan in 2008 called for the development and implementation of comprehensive nitrogen and phosphorus reduction strategies for states in the Mississippi River Basin. So the states are going through this process. Iowa has a strategy that's been developed. Minnesota has a strategy. Illinois is in the process of developing a strategy. Indiana has some materials out. And so that's really what has led to this action plan, and the task force in 2008 calling for these has really led to development of nitrogen and phosphorus reduction strategies for the states. And again, that phosphorus loading in our Great Lakes Basin, Lake Erie, one in particular, and the role that drainage plays in that is critical, and something we're going to be faced with looking at into the future. As we look at hypoxia, and we think of major events leading to the formation of hypoxia in the Gulf of Mexico, we see freshwater discharge and nutrient loading from the Mississippi River. We get nutrient-enhanced primary productivity, and that when that consumed or decomposes, we see consumption of oxygen such that within the Gulf of Mexico we get a zone of low dissolved oxygen, such that we get this hypoxic zone. So we have this nutrient coming down the river. It promotes productivity in the Gulf. When that decomposes, consumes oxygen. So as we look at the Gulf of Mexico hypoxia goals, the Hypoxia Action Plan goal developed by the Hypoxia Task Force calls for reduction in the size of the zone to 5,000 square kilometers by the year 2015. Now, last fall, the Hypoxia Task Force met in St. Paul, and they recognized that the timeline of that goal, the 2015 timeline, would not be met, but they still recognize the goal, the size goal, to be 5,000 square kilometers. Now, in about the 2008 timeframe as well, EPA convened a Science Advisory Board panel to review the science behind Gulf hypoxia, to develop recommendations for reducing the size of the zone, and ultimately then that led to recommendations for reduction in total riverine nitrogen and phosphorus loads of 45%. So each of the states or all the Mississippi River Basin, the recommendations are to reduce nitrogen and phosphorus loadings down the river by 45%. And we'll talk a little bit more about that, but that's certainly a goal that is out there, a fairly large goal, but something we need to recognize. As we look at the graph that you see here, those light blue bars are the May dissolved nitrite plus nitrate flux into the Gulf of Mexico. And so you'll see that vary, really a low in the last 20-some years of 1998, also 2012. So that drought year of 2012, low loading down the river to the Gulf in May. We look at 2013, we see a large loading. As you look at the blue line on that, that's the hypoxic area. That's data from Nancy Rabelais, but that is the estimated hypoxic zone area in the Gulf. And so you see that vary from year to year. 2012, for example, a year with a smaller size, really likely due to less loading down the river in that year because of the drought. So, really that flux down the river is critical, and the size of the zone can be fairly strongly tied to the flux that's come down the river. So as we look at kind of dissolved oxygen contours, I just have 4 slides here looking at the dissolved oxygen contours in the Gulf in 2010, 2011, 2012, and 2013. So you can kind of see where we see the area with low dissolved oxygen, and also kind of the size of the hypoxic zone. So, and when we talk about hypoxia, we're talking about areas that have a dissolved oxygen concentration of less than 2 milligrams per liter. So as we look at this, those areas that are in red and dark orange, so we look at this region right in here, red and dark orange, those are our areas where the concentrations are less than 2 milligrams per liter of dissolved oxygen. And now as we go on to 2011, again, this is a year we see fairly large areal extent of kind of the orange and red area, that low dissolved oxygen area. So we see here kind of all these areas have under that 2 milligram per liter of dissolved oxygen. Now, kind of keep that 2011 map in mind, and we contrast that with the 2012 map, even though now there's some data from Florida as well, or from off the Florida coast, but you'll see much smaller zone. You know, as we look in this region, a lot smaller area with that low dissolved oxygen. In fact, the area of less than 2 milligrams per liter is quite small in comparison to what we saw in 2011 or 2010. Now, if we look at 2013, again, we see a larger size, at least in comparison to 2012. 2013, we saw more loading down the river, more flux of nitrate and phosphorus because there was more water flow that was coming down the river. A wet year compared to a dry year. And so we see in this zone off the Louisiana coast, fairly large areal extent with the dissolved oxygen concentration less than 2 milligrams per liter. Okay, so we've kind of highlighted hypoxia, maybe some of the issues there, and the goals for reducing loading of nitrogen and phosphorus down the river. So as we kind of look up in the watershed then and estimate that percent of the area benefiting from drainage, what we see is that there are many areas in the Mississippi River Basin with a high percent of the area with land benefiting from subsurface drainage. We also see that in some of the Great Lakes Basin, as well as going up to Lake up into Canada in the Red River Valley of the North, up in this area. Now, some of these areas, the land benefiting from drainage may benefit from surface drainage rather than subsurface drainage. But as we look at the areas across the Corn Belt, from Minnesota to Iowa, through Illinois, Indiana, and Ohio, in these regions, most of those areas would be benefiting from artificial subsurface drainage. Certainly as we go up into the Red River Valley, into Minnesota, North Dakota, even South Dakota, there's more and more subsurface drainage in those areas. But a lot of southern Minnesota, Iowa, Illinois, Indiana, and Ohio, have been drained, fairly extensive artificial subsurface drainage for well over 100 years. And so, again, this is a map that Dan James and David James at the USDA Agricultural Research Service, the National Laboratory for Agriculture and the Environment here in Ames, developed, combining land use and the hydrologic class of the soil, so somewhat poorly drained and wetter soils, and then some slope characteristics as well. But we see areas within Iowa Illinois, Indiana, Ohio, up into Minnesota, up into to North Dakota and upper Minnesota there in the Red River Valley, with greater than 25% of the land benefiting from drainage, in many areas greater than 50% of the land benefiting from subsurface drainage. But when you combine that extensive subsurface drainage network with intensive crop production, what we see is high nitrate loss from those areas. As we're looking at nitrate, it's the primary loss mechanism for nitrate is water moving through the soil profile and then intercepted by a tile line and then short-circuited right to the stream. And so this is a map of estimated nitrate-nitrogen loss January to June for 1997 to 2006. This is information summarized by Dr. Mark David from the University of Illinois. And what we see is that those areas, if we think back to that previous slide on locations that had a lot of drainage, what we see are these areas in south central Minnesota, north central Iowa. In that region, a lot of subsurface drainage. Also, intensive crop production. We see a lot of nitrate loss, nitrate export from those areas. Similarly, as we look at Illinois, Indiana, and parts of Ohio, we have a lot of drainage, we have a lot of row crop production, we have a lot of nitrate loss from these areas. So as we think about hypoxia, we're concerned about that nutrient loss. We think about our drained landscape. It can short-circuit that nitrate loss, short-circuit some of that nutrient loss to the stream. So what are we going to do about it? Well, one question and maybe a challenge is, what about nutrient management? And certainly that's a critical factor, but as we start thinking about drainage water management, I just want to highlight maybe why we need something like drainage water management or some of these other edge of field practices. So this is a data curve. The curve is from some data that we collected in north central Iowa, published in the Transactions of ASABE, American Society of Agricultural and Biological Engineers, in 2008. And then the other data points are other data sets from Iowa and south central Minnesota. And really what we wanted to do here is, how does our nitrogen application rate to corn in a corn-soybean rotation influence the nitrate concentration, the flow-weighted annual nitrate concentration that we see coming out in a tile line? And this, the flow-weighted annual nitrate-nitrogen concentration is really the combined concentration from the corn and soybean phase. So we're just applying the fertilizer to the corn phase, but we're looking at the response to that corn-soybean rotation. And what we see here is that if we look at Iowa, our estimated average application rate to corn following beans is about 150 pounds of nitrogen per acre. And we see if we had 150 pounds, our long-term estimated flow-weighted annual nitrate is just slightly over 13 milligrams per liter, 13.3, I think, to be exact on that curve. Now, if we reduce that application rate to, we'll say 135, we see our estimated flow-weighted annual nitrate concentration is about 12. So we get a little over maybe 10 to 15% reduction, probably closer to 10% reduction in flow-weighted annual nitrate if we reduced that application rate to what at least some would consider a recommended level, which is the maximum return to nitrogen. That 135 for the maximum return to nitrogen is for Iowa. It's for $5 corn and 50-cent nitrogen. It would adjust based on what that ratio of price of nitrogen is to the price of the corn. But what this highlights is that even if we used the recommended amount of nitrogen, we still could see nitrate concentrations in excess of the drinking water standard, which is 10 milligrams per liter. And, by this scenario, only about a 9 to, 12 some percent reduction in nitrate, where our goal is 45% reduction. Also, to kind of highlight on this, maybe the challenge of just doing this with nutrient management in many of our areas is that even if we went to no nitrogen, so we went to no nitrogen application in a corn-soybean rotation, we still see concentrations of about 7 parts per million from our corn-soybean rotation. Now, if we had a perennial-based system, it'd be much lower than that. We have data that documents that. But within a corn-soybean rotation, we still see somewhat elevated levels of nitrate nitrogen, such that we're only getting about a 40 to 50% reduction. Even if we went from our average nitrogen application rate of 150 down to 0, we're only getting about a 40 to 50% reduction in nitrate. This really highlights why it's a challenge, or it would be a challenge in many areas of the Corn Belt to reach a 45% load reduction goal with just the nutrient management, with just in-field nitrogen management. That kind of brings up the need to look for other practices that can help us from a water quality perspective. Things like cover crops, things like subsurface drainage bioreactors, things like wetlands, things like resaturated buffers, and then things like drainage water management, which we're going to get more into right now. So as we look at drainage water management, the objectives of what we're doing, we want to conserve soil water, potentially have a positive yield benefit to the crop, and reduce losses of nutrients and other pollutants via that subsurface drainage system. In many of our areas, we're specifically concerned about nitrate nitrogen, but as we get into the Great Lakes basins, we may be also concerned about the phosphorus coming out of that drainage. So as we look at it, the concept is water that would drain out of the soil profile under conventional or free drainage is conserved within the soil profile and available to supply evapotranspiration requirements of the crop or of the system in general. So as we look at this and think about this from a agricultural field perspective, here's our kind of a simplified version. We have our tile line. You can see kind of how most of them are functioning, free flow out of the system. Okay, instead of that, we put a control structure in. Right there, there's our control structure. Okay, in the mode it's in right now, it's a free flow system. We have the control structure there, but we're not altering the flow at all. One thing to keep in mind if you're talking to producers is drainage water management is not plugging the tile. So as I've talked to producers, some say, I'm not going to plug my tile. No, we're not plugging the tile. All we're doing is we're putting some stop logs, weir plates, whatever we want to call them, within our control structure right here. So we have our plates in there. We put those plates in place so that water has to build up behind those plates before it flows out to the stream. So we're kind of using the soil back here as a natural reservoir and managing the water table back in our field to try to hold some of that water back. So after harvest, we may put those outlet boards in place so that we can raise the water table, provided that there is water there, provided that we get rainfall and have that water table build up. So we'd store that water in there. Outlet raised after harvest to reduce winter loss, winter delivery of nitrate to the stream. Well, then for crop production, shortly before we're wanting to do planting, maybe a couple weeks, we pull those outlet boards, or we pull those boards up and out of the way so that our system can function as a free drainage system. So we just get the free drainage flowing through the control structure without any alteration. Then after planting, after some of our early crop development, maybe after spraying, we're going to put those stop logs back in place, maybe not up as high as we do in the winter months, but maybe within 2 foot of the ground surface, and store water back in the soil profile. Again, provided that there is water to store. One of the factors here is we're not under drainage water management. Drainage water management is different than sub-irrigation. Sub-irrigation, we might put water back into the system. With drainage water management, we're relying on rainfall and storing some of that rainfall water, excess precipitation, within the soil profile. And so in this case, the only way we'll build up that water table is if there's excess precipitation that builds that water table up. So in a year like 2012, for example, in Iowa, we did not have precipitation in June of that year to store. So we didn't alter that water table at all because there just was not water there to store within our soil profile. But in some years, we may get a little excess precipitation in June that we can store a little bit of that water going into the July and August period, when having an extra half an inch or inch of water might provide some benefit. Okay, and then before we get to harvest, we'd pull those plates up again so that we make sure we maintain trafficability and such in our crop field. So a couple things here is, one is we're not plugging this. We just have a control structure with stop logs in there, or weir plates or boards in there that the water builds up behind and then flows out of our system. We'd want to pull those plates before planting, before harvest, so that we're not impacting those field operations that would happen during those times of the year. As we look at some of the results that we've seen from this practice, and this is information from different states in the region. This is primarily data from a conservation innovation grant funded by the Natural Resources Conservation Service, and the Agricultural Drainage Management Coalition was really the entity that got the grant from NRCS to do this work, and then individual investigators in each of the states worked on this. And so we have data from Ohio, Indiana, Illinois, Iowa, Minnesota, and then kind of combining all of these. And what we see is kind of a range in drainage outflow reduction of maybe slightly under 10% in Indiana, all the way up to a high of 60% in Ohio. So if we look at on average, we're seeing about 35% reduction in the volume of water on an annualized basis coming out of that drain. Okay, if we look at the nitrate load reduction, again, we see about a 35% reduction in the amount of nitrate, or pounds per acre of nitrate, that are lost from a field where we have drainage water management compared to conventional or free drainage. All right. So really what we're seeing is no change in nitrate concentration. As we look at the data from these sites, we see very similar nitrate concentration of that water where we have managed drainage compared to where we have free drainage. But since the pounds per acre of nitrate loss are a product of how much water comes out and the nitrate concentration, if we're reducing the volume of water by 40%, say, then we're reducing the nitrate load by 40%. And really that's what we see. In general, we see very similar nitrate load reduction percentage as we do drainage outflow reduction percentage. So as we look at this, all told, we're somewhere in that 30 to 40% reduction in the volume of drainage and nitrate load from these systems. Now, as we look at crop yield increases, really we see maybe little overall benefit from the studies conducted so far in these states. We see maybe a high of about 4% here. So we're, in this case, we're referring to the right y-axis, and so that's about 4 to 5% yield increase, and we have a low of maybe minus 1% or in that ballpark for the crop yield impact in Minnesota. Our site in Iowa, we see essentially no impact. on the crop yield where we have the managed drainage compared to where we have the conventional drainage. Now, this is going to be very year dependent. For example, in Iowa, the data that was summarized in these, all but one of those years were wetter than normal. We had wet periods throughout most of the summer. Those would be years when we wouldn't expect much benefit, yield benefit as well, or yield benefit from the managed drainage system. Because if we're wetter than normal, we probably have very little drought stress on the crop, such that having a little bit more water is not going to provide much benefit, and we didn't see much benefit. So I like to think the years where we might see some crop yield benefits are years where, maybe it's fairly moist in June, and then that we're able to store some water in the profile, and then it gets drier in late July, early August, and we've stored some of that water. But a year that's very wet, we're probably not going to get much benefit. Also, a year that's very dry, there's no water there to store, so we wouldn't expect a benefit there. And that's really what we've seen. In 2012, we were not able, at least in Iowa, we were not able to maintain the water table because we just did not have any water there to maintain. Okay, so now we've kind of talked about the issues, why we might want to do drainage water management, what might be some of the benefits, what the performance is that we've seen. The next question might be, how applicable is it throughout the Midwest? And so this is a map developed by NRCS, by the National Technology Support Center, Central National Technology Support Center. And this is the estimate of the cropland suitable for drainage water management. Looking at slopes less than 1%, and looking at soils that are estimated to benefit from drainage. And what we see is that we kind of see a range, kind of in that applicability. We see a fairly substantial, area up in the Red River Valley of the North there, with the applicability of the practice. And certainly if you've been up in that region, it's very flat. And so I like to think of drainage water management works better on sites that are very flat, maybe uniform flatness. As we look at south central Minnesota and north central Iowa, this would be what we term kind of the Des Moines lobe, some of that prairie pothole area. We see, fair bit of blue in that area, indicating cropland suitable for drainage water management. I think one of the challenges in some of those areas might be some of the depressions we have. And so the field might be fairly flat, but we may have some depressions in some of those areas. And so I think that we might have a little bit more challenge to get the drainage water management installed in those areas than on a uniformly flat field. And so as there are the on-site training in those areas where we have some of those undulating soils, it's something to really think about with the design. I know in Iowa, we're having one of the sessions in Pocahontas in north central Iowa, and we'll talk about that. I think that also kind of brings up a point about the design of these systems that could be critical, and that's that the time to do drainage water management design is at the start of kind of the drainage project. Rather than waiting till 2 years after the drainage system is already in and saying, oh, I want to do drainage water management. Well, you may not have laid out the drainage system to really accommodate drainage water management. So the time to really think about drainage water management is at the time of drainage installation. Certainly there are going to be some cases where the drains have been in for 5, 10, 20 years, maybe a pattern drainage system in that long that we try to retrofit. But I think we really, as each drainage system goes in, we want to be thinking about drainage water management and how do we do that design now rather than 2 years down the road and then find out that, oh, this doesn't accommodate drainage water management very well. Okay, as we look across Illinois is probably the state actually is the state with the greatest acreage estimated to be suitable for drainage water management. In fact, by this estimation technique, over 10 million acres are estimated to be suitable for drainage water management in Illinois. And then we can see as we go into Indiana and Ohio, even up into areas of Michigan, we have some more area that is estimated to be suitable for drainage water management. So as we look at this, Illinois, again, estimated applicability on greater than 10 million acres. Indiana, about 2.7 to 2.8 million acres. Iowa, about 4 million acres. Missouri, about 1.8 million acres. Michigan, about 1.2 to 1.3 million acres. Minnesota, I guess, would be second only to Illinois, because Minnesota, it's estimated about 6.3 million acres. And when you consider the south central Minnesota area and the Red River Valley of the North, we get that 6.3 million acres. Ohio, just a bit over 2 million. South Dakota, maybe about 200 to 300,000 acres. Missouri, a little over 300,000 acres, and then North Dakota, about 1.2 million acres. These are some estimates for cropland suitable for drainage water management. So again, not each state would have the same amount of area suitable for it. Not each part of a given state would have the same amount of area suitable for this. So this is really a practice that is most applicable to some of our flatter areas, and so we need to be kind of targeting maybe some of our work with producers in those areas to try to get as much implementation of this practice as possible. Okay, that kind of gives kind of the background and on drainage water management, maybe why we're going to do it, what might be some of the benefits, and where it might be most applicable. Now, if we look at the rest of the online training modules, training curriculum, the next module is going to be on drainage concepts and tools. That will be developed by Dr. Chris Hay from South Dakota State University, and he'll talk about soil property, drainage needs, drainage intensity relative to depth and spacing, and sizing of the tile, and then some of the design tools that we might use. After that, a presentation by Dr. Kelly Nelson with the University of Missouri, talking about the drainage water management planning process, what you need to know when you're talking to the producer, what information is needed, kind of goals and objectives in working through that planning process. Next module on drainage water management concepts and land suitability by Dr. Richard Cook. He'll talk about the purpose, more about these benefits from an effectiveness and nutrient reduction, what resource concerns are addressed, and how this might work into other conservation practices as well. Then Tom Scherer from North Dakota State University will talk about water control structures, looking at typical structures, how to design them, thinking about the structure itself for a drainage water management system. Then drainage water management layouts, new and retrofits, and so this is where you kind of get to think about how we design that system maybe differently than we would if we were just thinking about conventional drainage, and how might we retrofit that. So Dr. Gary Sands will have a module, is developing a module on facilitating drainage water management, making sure there's no negative impacts on surrounding neighbors, and thinking about how we design and lay out the drainage system to facilitate drainage water management. And then Dr. Larry Brown from The Ohio State University will talk about operation and management of that drainage water management system. What kind of operation and management needs to be done to accomplish producers' objectives, as well as to meet the Conservation Practice Standard 554. Considerations on sodic and saline soils, thinking about what are the hydrologic, maybe a little on the hydrologic impacts of drainage and how the management might impact that. And last, but certainly not least, is a presentation by Dr. Jane Frankenberger from Purdue University that'll be talking about related conservation drainage practices. So there are other things that we can do kind of at the edge of the field to help us reduce nutrient export. And so we talked about drainage water management. That's kind of one of those edge of field practices in many ways. But we have others. Denitrification bioreactors. So the wood chip trench, where we're enhancing denitrification and removing that nitrate and sending it off as nitrogen gas is one thing she'll talk about. Wetlands that are specifically sited and constructed to promote denitrification and convert that nitrate in the water to nitrogen gas. That's another one. Our two-stage ditches, saturated buffers, and sub-irrigation would be some of the others that would be included in that. So as we kind of wrap up this training module, if we think about why we are here, drainage is something that is very important for crop production throughout the upper Midwest. But with that drainage comes a mechanism for which dissolved nutrients can be lost, short-circuited to downstream water bodies. So we need to be looking at ways that we can reduce that nutrient loss from the drainage system to downstream water bodies. This is becoming of increasing concern because of issues such as hypoxia in the Gulf of Mexico and nutrient loading to the Great Lakes in the U.S. So there is a sense of urgency right now. There's a sense of urgency through kind of some of these state nutrient reduction strategies that there is a need and an urgency to get implementation of practices that can reduce nutrient loading. There's a sense of urgency as new drainage systems go in. Now is the time to incorporate drainage water management into that design. So we talked about doing drainage water management 2 years after the drainage system has been installed is probably not the best way to do it because we may not have laid that drainage system out to readily accommodate drainage water management. In that case, we may have a retrofit and it may be a lot more difficult. Gary Sands will talk more about that as you move forward. And I think as we move forward, thinking about those areas of each of our states where drainage water management may work best and trying to do appropriate training and education in those areas may be critical, because from our applicability map, we certainly saw that some areas of each of our states have kind of more area than others. So if we look at that blue map, there are larger areas of blue in certain areas of each of our state than others where drainage water management may be applicable. And so I think that is another critical factor that we want to consider as we move forward. Where are the best places to do it? And then we can think about how we engage those producers to get them to implement these practices. So hopefully you got something from this module, and I think all the rest you'll get more in depth into the drainage water management concept. This was to just kind of provide an overview, give a context of why we're worried about this. Certainly, again, we're worried about the water quality side from the nutrient loss from our drainage system. Drainage water management, again, in some areas could provide a little bit of water that might meet some transpiration demands of the crop throughout the growing season. So certainly a practice that producers and landowners may have some interest in, and we need to think about and be prepared to help them with the design, the operation, and management of that system. And so